to copy this example down. We're continuing at section 6.2 of volumes. And let me give you a moment to copy the example down. Okay, so let's see what we have here. Now, we want to find an expression for the volume of the solid obtained by rotating the region enclosed by the curves y equals x squared and x equals y squared. And we're going to rotate this region about the line x equals -1. Now, as x equals -1, is that a horizontal line or is that a vertical line?
Vertical.
That's right, Maria. It's a vertical line. It's a vertical line. So, okay, how would we start? I mean, how would we start this problem, class?
Graph the functions.
That's right. We have to. That's right, Renaud. We have to graph, make a picture of this. Okay, so I'll show you a picture on the next page. Has everybody had a chance to copy the example down well? Okay, Sean's good. Let's make sure here. Samuel's good, excellent. Jacob's good, wonderful. Nathan, all right, let's go to the next page. Okay, here's my picture. Okay. All right, so, and obviously it's going to take you a little time to copy this, but here's the region bounded by y equals x squared and x equals y squared. Okay, that's this region, and I'm taking that region and I'm rotating it about the line x equals -1. So x equals -1 is here. And of course, this is the mirror image of the region. And it's being rotated, right? It's being rotated about the line x equals -1. So I'm just kind of getting the picture. you know, filling in a few little details. Okay, and it's this region here, right, that we're rotating. So I'm not sure how we would describe this volume that we're getting. Like a, I don't know, funnel cake. I'm not sure what you know. I mean, we can picture the volume in our minds, but I'm trying. Sometimes I try to think of what the volume might resemble. But let me give you a moment to copy now the picture down before we proceed on. If you have any questions, please let me know.
You could say that it's a canoe with no middle. It's just the ends and the top and the bottom, right?
Or it's just a diaper.
I didn't think about that. A canoe. What'd you say, Samuel? What'd you say?
A diaper.
A diaper? Well, you know, I mean, I guess based on your experiences and what you've seen in life, I mean, I can understand a diaper or a canoe. It's the volume is a volume going around in a circle. It's taking this region and going around in a circle. A bowl with the bottom cut out. Sure, Sean, that's a possibility. So all of these are possibilities. And so remember that when we find like the volume, see, we're rotating. Since we're rotating this region about the line, the vertical line x equals -1, it's helpful to picture the volume by thinking of it as taking this outer volume here, which is the volume of a bowl with the inside included, and then cutting out this volume here, which looks like a frustrum. Not quite a frustrum, but if you take the difference of the outer volume and the inner volume, and you know, the outer volume is the outer volume because it comes from, like, here's the outer part here, right? There's the outer part, and that's going to generate this outer volume. And then the inner volume is defined by the x equals y squared function. And so this is your result. And what we have to do is, if we can find expressions for the outer volume and the inner volume, we just take the difference. Well, it's clear that we have to find the radius. We have to find the radius for each of these volumes. And you can see what I'm doing here is for the outer volume, well, let me ask you this. Is it better to integrate with respect to y or x here? I mean, actually, there's only one right answer. Or would we integrate with respect to x or y?
Y.
That's right, Liping, with respect to y. Because look at the radius. Look at the radius here. Okay. If I circle this here, let's talk about the outer radius. So the outer radius, I have, and remember, you can use the zoom button on your right to blow up the picture. If I take the square root of y minus -1, okay, well, and where am I getting the square root of y? Well, for the outer radius goes from, let's see here, I want to just, I'll do blue here. It goes from the axis of rotation all the way to the outer function. The outer function is y equals x squared, or x equals plus times the square root of y. Well, if I take the distance of this radius, is the radius a horizontal distance or a vertical distance? The radius. Is it a horizontal radius or a vertical radius?
Horizontal.
Horizontal. Okay, well, if I'm going to find distance, if I'm going to find the distance, okay, between 2 points horizontally, okay, like if I'm finding the distance between 1 and 7, okay, that's going to be 7 minus 1. Okay, that's 7 minus 1, but that's with respect to an x-axis, right? A horizontal distance, okay, when you learned algebra, if you have 2 points on the x-axis, 7 and 1, the distance is 7 minus 1. So I have to say, okay, well, my distance is going to be the difference between -1, that's the x value here, and the x value here. Of course, this x value is greater than x equals -1. That x value is x equals root y. And that's going to change depending on where, you know, that's a function of y. But that's how I get the square root of y minus a -1. That's that's how I get the outer radius. And so the outer radius here, maybe I'll just add the words. One moment. The outer radius is square root of y plus 1. Okay, because that's equivalent to the square root of y minus a -1, which is equal to, you know, the outer radius. Now the inner radius on the other hand would be this. Well, maybe I'll put it in red. Like this, the difference between these two x values. Well, the value on the right goes with x equals y squared. The value on the left goes with x equals -1. So here you have y squared minus -1. Okay, are there any questions on how I'm getting, and then I'm integrating with respect to y. Are there any questions on how I'm getting my outer and inner volume here? Please let me know if you're uncomfortable.
So if you were rotating about like y equals -1, then you would want to integrate with respect to x instead?
That's correct, Maria.
Okay.
That's correct. Very good. Very good. All right. Are there any other good questions before we move to the next page?
I couldn't quite hear what Maria was just asking. What did she ask?
Oh, Maria, go ahead and repeat what you said there.
So if we were rotating it about y equals -1, then we would need to integrate with respect to x instead.
And that's correct.
Mm-hmm. Okay.
That's
Thank you.
correct. All right. You're welcome. Are there any other good questions? Okay, well, let's evaluate this. Let's evaluate this. Okay, and so we'll go to the next page. And I put in some details for you. Okay, so we had here the square root of y plus 1. Well, I'll write it in. We had here square root of y plus 1 quantity squared. So if we use FOIL, we'll get then the square root of y squared plus 2 root y plus 1. And similarly, that was for the outer volume. The inner volume was, we had y squared plus 1 squared. And you know, we have the pi here. We have the pi there. We talked about that last time. The book, we derived why these, you know, pi r squared is the integrand for these volume problems. And we showed that in the last class. So anyway, you know, I carefully FOIL. And then this is just a matter of just being careful with your work and your integrals. Let me know if you have any questions. So key to these problems is drawing a picture. That is key to these kind of problems. Many a man and a woman has tried to solve these kind of problems without drawing a picture, and it never works. All right. Are we ready to move to the next page? Let me know. Okay, Jacob. All right. Very good, Leping. Okay, very good, Jacob. Okay, Jazi. Yes, Samuel.
Oh no, I just clicked twice by accident.
Oh, you're good. Okay, excellent, excellent. All right. Okay. So let's get an answer here. Let's go ahead and continue the computation. Okay. And this is just computation. The volume of that canoe or bowl, like the actual material of the bowl or the diaper, the actual true volume is 29 pi over 30. And that's the answer WebAssign's going to want. So, but let me give you a moment to copy this down. Let me know if you have any questions. I mean, it really is quite amazing. I mean, this is the exact volume. And it matters getting the exact volume, right? Volume of material used. Material's money, right? Places like grocery stores, sometimes it's, you know, their margins are very tight. So companies, when they make things, they can have very tight margins. So the exact volume of material being used to construct something, you can understand how important that is. And actually, this concept of volumes came up in the 1700s because people wanted to find volumes of wine barrels. You know, wine barrels don't have your standard shape. And, you know, Nathan, question?
Yeah, can you go back to the page previously, just for a second?
Sure. Okay, all right.
Okay, I understand now. Thank you.
Okay, no problem. All right, are there any questions before we move on? Okay, well, let's move on. Let's look at another example. Okay. And let me give you a moment to copy this example down. Okay, so here we want to find the volume of the solid obtained by rotating the region enclosed by the curves y equals 2 plus the secant of 3x. And this is we're restricting x to be between negative pi over 9 and pi over 9. Hold on here. Let me just do that again. Hold on. This is the one curve. And then the other curve is y equals 4. Okay, so we're going to rotate this region about the line y equals 2. And what's the first thing that we need to do to solve this problem?
Graph.
We have to do a graph. That's right, Jacob. That's right, Renat. We have to graph it. Now, the secant of 3x, okay, the secant of 3x. So we could use the TI calculator. We could use Desmos. How's the secant of x defined?
One over cosine.
That's right.
1 over cosine.
1 over the cosine. Good. Good. 1 over the cosine. Okay, so like for instance, the TI calculator doesn't have a secant button. So what you'd have to do is you would have like, you'd graph two functions. The first one would be y equals 2 plus the cosine of 3x. And then you can limit your domain here, right? And then the second function is y equals 4. And then y equals 2 you can graph also. So let me show you what that would look like. Okay, I know you can graph things, so I'm not worried about you graphing it. I know you can do it. Be sure when you do graph it, since it's a trig function, what mode should your calculator be in?
Radians.
Radians. Okay, good. Good, Maria. Good, Jacob. That's right. So, okay, here's a picture. Here's a picture. So let me show you here what we got. Here's y equals 4. Here's y equals 4. And then here's the function y equals 2 plus the secant of 3x. So this is our region. And we are rotating that region about the line y equals 2. So of course the origin is here, right? And y equals 2 is here. And so the mirror image of this region is here. Okay, and we're rotating it about, well, I'll just kind of highlight this here also. So I wonder what, I mean, here's the region that we're rotating about the line y equals 2. Gosh, I'm trying to picture what that, I mean, I know what it is in my mind, but I'm trying to think in real life what it resembles.
An apple that you ate the core out of, like.
Well, but here,
A sideways nuclear reactor.
A sideways nuclear reactor. I don't know. I don't know. Maybe. The thing is that the side of this, like inside here is like an apple core. It's like taking an apple core. Okay, Sophie, here in the apple core. Take like a can and cut out a part of the can that looks like an apple core. And and the volume that's left is what you have. So like this is like what I'm trying to say down here. Hold on. Like this here, outer volume minus inner volume. Now, not all the problems that you're going to have are outer volume minus inner volume, okay? But some of the problems will be like that, obviously. And this one is. Okay, so what I do here, by the way, is I try to justify why, like you see the coordinates here. This coordinate here is pi over 9, comma 4. And this coordinate here is negative pi over 9, comma 4. So why is that? Well, if we take that's the intersection of the two curves. So if 2 plus secant of 3x equals 4, we'll end up getting that cosine of 3x equals 2, or equals a half. Cosine of 3x then would equal the arc cosine of a half. And the arc cosine of a half would be plus or minus pi over 3, because the cosine of 60 degrees is a half, and the cosine of 60 degrees is a half, and the cosine of negative 60 degrees is also a half. Okay? I mean, in terms of like if I just draw, an x and y axis, the cosine is equal to a half in quadrants 1 and quadrant 4. Okay, so there's two angles here, pi over 3 and negative pi over 3, whose cosine equals a half. And hence x then, if you divide by 3, x equals plus or minus pi over 9. So I just included this, one moment, I just included this to justify, how they're getting these angles that you've probably never even seen before in your life. You're used to pi over 4, here. I didn't even notice that. I have it there. I forgot about that. Okay, so now we get to the radius. So the radius for this, there are two radii. There's an outer radius and an inner radius. So the outer radius is going to go from 4 to 2, or I should probably draw it this way, from the axis of rotation, which is 2, all the way up to the outer function, which is 4. Well, 4 minus 2 equals 2. And then the inner radius goes from the axis of rotation, y equals 2, to the inner function, which is y equals 2 plus secant of 3x. So if I take 2 plus secant of 3x and subtract 2, that gets me secant of 3x. And so now I have my outer radius and inner radius. And, I got to evaluate all this. I got to evaluate this volume. The limits, of course, go from pi over 9 to negative pi over 9, and I'm integrating with respect to x because I'm rotating about the horizontal axis there. And now it's just a matter of computing. So you really want to take your time on these problems, right? Because it definitely wastes time if you don't have your integrals right, and then you go through the work and get the wrong answer. You don't want to waste time. So you want to start off carefully, as always, and try to get the right answer. Any questions before we? So this problem is not in the, it's not in the one of the examples, but you'll have one like it in your homework. Again, I try to do a variety of problems for you so that, you know, sometimes I like to do ones that are in your homework or ones like in your homework, just so you have a you know, wider variety of examples. Well, which integral is going to be harder to do? The first one or the second one? Which integral is going to be tougher? Second integral. I agree, Jacob. And it's good we know our integration techniques. Absolutely good. All right, let me know when we're ready to move to the next page. If you take multivariable calculus, you'll learn how to compute volumes as well. All right, thank you, Samuel. But you'll be using double and triple integrals to compute volumes. How many of you have to take, oh, question, Samuel?
Yeah, so where did we get this 60-30 triangle from in this case?
The 30, 60, 90 degree triangle from?
Yeah.
Here, well, this is something that sort of it's normally covered in trigonometry. But I will tell you, in the textbook, there's an appendix C in the appendix that appendix C is a section on trigonometry, and if you look in appendix C, look at, I'll actually locate the figures now.
No, I'm saying, why is it relevant? Why is it relevant here?
Oh, well, what I wanted to do is I wanted to, it has to do with this. It has to do with this. Here, you see how I go from here to here. See me highlighting that? Why is the arc cosine of a half equal to plus or minus pi over 3? Well, here's the justification. Angles of 60 and negative 60 degrees, their cosines will both equal a half. And so that's just to justify this step here.
Oh, okay.
Okay.
Let's see. Thank you.
All right. All right. Good question. Are there any other good questions? Okay, well then let's move on. We got to integrate, we got to find this volume. So, okay, I'm going to make a substitution on the second integral. Okay, I mean, I know the antiderivative. Well, what is the antiderivative of secant squared, class? Do you remember? From your calculus 1A? That's the tangent of x. That's right. Good, Samuel. But see, I don't have the tangent of x here. I have the tangent of, I'm sorry, I don't have the secant squared of x here. I have the secant squared of 3x. Okay? Makes me a little nervous, right? So I want to handle that. I'm gonna do a substitution. I'm gonna let u equals 3x, then du is 3 dx, then dx is equal to 1/3 du. So that means then that this second integral here this second integral with respect to x through that substitution, u equals 3x, I can convert that second integral to an integral with respect to u. Okay. And now I'll have secant squared of u, which I'm happy about because I know the antiderivative of secant squared of u is going to be tangent of u. But now the limits are pi over 3 and negative pi over 3. Have to change the limits, they're u limits. How do I get pi over 3? Well, 3 times x, 3 times pi over 9 is equal to pi over 3. And 3 times negative pi over 9 is equal to negative pi over 3. Okay, and now, you know, in the first integral is no problem, you know, doing that. Just see here. It's really beautiful stuff, really is. Applications of integration. Just see one thing here. Yeah, so then I just, you know, get the antiderivative of the secant squared, which is the tangent of u, and I just proceed forward. And the answer in the end is going to be 8 pi squared over 9 minus 2 times pi root 3 over 3. Yes, Nathan.
Was the lower bound always negative pi over 9? Or did that get changed? Like on the first equation?
It was negative pi. Oh, I'm sorry. Let me see. Let me check. Let me check. It was. If we go back, I'll come back to your class. Hold on. Here, the lower limits were negative pi over 9. Yep.
Okay, thanks.
No problem. All right, please let me know if you have any other questions. Okay, now, is this final answer, must it be positive? If you were to put that, I mean, now WebAssign would want that answer, right? It wants an exact answer in simplified radical form because that's the best. But if we were to convert that, I mean, well, if we were to, you know, try to approximate that with the decimal, we would get a positive answer. Should the answer be positive for these section 6.2 problems? Should the answers always be positive?
Not if you're rotating about the y-axis, right? I'm sorry,
Well,
the x, if you're going negative.
well, but we're always computing a volume, and in this case, I mean, the volume has to be positive. I mean, I understand, like you learn, like, for instance, areas. If the area is below the x-axis, it's negative area. If the area is above the x-axis, it's positive area. But in this case, you are actually computing, you're finding volumes of solids. The volumes have to be, they have to be positive. They have
That's
to
what I
be
was
positive.
confusing myself with, was area.
Yeah, yeah. Well, and this is why, you know, and I appreciate, you know, all responses, all input, because, you know, it helps make a better class. You're comfortable with that, Maria? You're comfortable now that the volumes,
Sure am.
good, good. And, you know, I'm thinking, you know, your next exam, which incidentally will be available next Thursday, right, July 1st. That's when exam 2 is coming around next week. You know, if you're doing a volume problem, and you get an answer, do you think it, like, before you submit an answer, it might be good to sort of to check if the answer is positive? Do you think that's kind of a, how many would maybe do that just as a little check? If they, okay, Jacob would, and the Ping would, and, you know, just little things, because sometimes, you know, people get things flipped around, and you know, so the student might accidentally do inner volume minus outer volume, right? And you know, so hey, if you can get it right on the first try, why not, right? Okay. Are there any questions on this? How many think this is really pretty beautiful stuff, what you're learning here? Okay, Jacob's liking it. Sean's liking it. Baraka, Sophie, excellent, excellent. Jazi, wonderful. All right, all right. Well, let me just give me just one moment here. I'm gonna stop the recording.